just for pictorial purposes, it's easier to draw rather than having two, pieces of the same kind or. Okay. Any other questions? Yes.
The critical points on the torus, two of them have index 1, which is a rational constant.
Yes, they have index 1, but as you see here that.
So similarly, if I look at the global maxima and the global minimum,
Yes.
what's the reasoning for the 2 and 10?
Oh, what's the reasoning? So I haven't given you a formal reasoning because I haven't defined it. My reasoning currently was to look at sort of the dimension of flow lines which flow down from that point. So if you are here, if you are given any tangent direction, no matter which direction you start driving, by gravity you are going to flow down, no matter which direction. That's a two-dimensional work of surface. Right? Whereas here, if you are here, you cannot really go down because you have to be in the space. So that's 0. Here you only have one direction where you can go down, and then one direction coming to it. So that's why individual expression for the number 1, 1 and 2 and 7. But once we define the Hessian and so on and so forth, we'll see that the index will turn out to be some linear algebraic quantity all over the C. And it will turn out to be independent of the coordinates in each node. Yeah,
Here we are choosing a function, and then actually from that we are taking out certain topological information out of that, and from the positions of the critical. But if we just get a random topological space, and so from that, how do we design that function?
Oh, how do you design? Okay, that's a good question. So it turns out that see, when you say random sort of space, ideally you imagine that space to be typically living inside some inferior space, even if it's a large inferior space. So there are theorems which guarantee that such a thing will happen. Right? So Whitney-Everett theorem says if you have a manifold, it lives in R to the 2n, for example. It's not the best form, but you can embed it. So in fact, that's how in some books you start defining manifolds. Now the point is, once your manifold lives inside some inferior space, you can project that manifold onto any line. And there is infinite family of lines, right? Lines not necessarily passing through them. You can project everything to a line. And it turns out that almost every such projection is a nice function. So the set of functions that we're considering is in some sense very large. There's no doubt of choosing such a function. Now if you want an explicit function, then that usually depends on how explicit your model is. This only guarantees that almost any such projection is a Morse function. Right? But I ask you which one, and you cannot pick one and say it's like a almost calculus. But here we are using S2 as a concrete x square plus y square plus z square is 1. Hence this function makes sense. And same thing here, write this down in a moment you see. I mean, all of you have seen a parameterization of this in the course on curves or something. So you know how to parameterize this. It requires two parameters, the inner radius A and alpha. The core radius A and this radius A. You need to parameter. Yeah, any other questions? Okay, so, all right. Yeah, so one remark I should have added here, now we will. Should have added is that and this essentially follows from I'll take that remark later. So I'm not going to make a distinction between F defined on a manifold or F defined on a local subset of Rn, because a manifold is locally Rn, so you basically use coordinates and can represent F. So let's see the critical point of F. And F, let's say R, which comes with its own set of coordinates. So let this be a local coordinate system. P. So for U, this is a global coordinate system. If your domain is a manifold, then you can only locally find coordinates. So we are interested in this one. At P. This is it's an N cross N matrix. So look at the matrix of the double partials. So there 2x by del x times del x at and we declare that to be the Hessian matrix associated with F. So this in Rn you might say, okay, since I have global coordinates which is already there, with a manifold which is a choice, so this of course will be dependent on the choice. So you don't have canonical. The point is that this quantity can be defined at a critical point even using vector fields by, because you know if you are given del by del x, these are nothing but vector fields in your manifold. So you can extend to given two vector fields, given two tangent vectors at P, you can extend them to vector fields and then you can define this to be acting on the function f itself by its combination, right? So it turns out that this is a symmetric. Well, in this case, it's symmetric by definition. But you can also sort of define the Hessian, which is what you might see in the course in geometry as symmetric linear map of PP. I'm just mentioning this point. And also defined as a map from the tangent space cross tangent space. Given two vectors, you extend them, and then you define this function by saying V acting on W acting on F minus W acting on V acting on F. And then of course you show that this is independent of the extension. But for us, for concrete, whether this is a genuine symmetric matrix, and the point is you want to look at critical points for which this is non-stable. So once you have a symmetric matrix, it's invertible. You can try to use various linear algebra that you know. So definition. And we'll do many examples. So critical point. This is what I meant by nice. Nice. So for those who are seeing this for the first time, it's a good exercise in change of variables to check that being non-singular is a well-defined thing. I'm not claiming that the matrix has the same determinant or the matrix is the same, they'll obviously not. You can scale coordinates and things. But this being invertible with respect to some coordinate system means this will be invertible with respect to any coordinate system. So that's what we mean by a critical point with non-invariant. So now I can define what a Morse function is. So function, and all functions, when I say f, for all purposes are smooth functions, which are synonymous with infinitely differentiable functions. So to read Euler's rule, he says differentiable equals smooth, so everything is differentiable up to whichever order you want. And for the most purpose, as you realize, this only requires activity C. Maybe for some purposes, we need C2. That's it's called Morse. If all critical points are not in. So the critical points are not too bad. They are sort of nicely sitting inside the actual space. That's it. So yeah, so before I state the first lemma, I mean, the proof essentially involves, it's not short, but the proof involves some fundamental theorem of calculus, some amount of diagonalizing in quadratic form, and some basic things like that. But you put everything together. So it's a nice proof, but you can either read it from there or you can think about it on your own first. But before I state the most lemma, let me go back to the two examples that we have here. Because our job, remember, is to understand what